All right. Well, look, welcome back. It's week 4, and we are going to be covering a few things this week. So we're going to be reviewing some submissions from the assignment, and then this week we're really going to cover what it takes to break a model into smaller pieces, right? So, so you've got something larger, and you want to be able to get it fitting on your print bed. What does that? What does that look like? How do you do it? What are the various techniques for doing that? And then, once you've broken it into pieces, how do you join it back together again, right? So, and then if you're working on a model that involves lots of smaller pieces, and you want to try to get the orientation right for strength, how do you build sort of snap together or piece together parts? I'll briefly dive into the Tinkercad specifics for making a thread. So literally making like a nuts and bolts, and then I'll get into some like fun art stuff with printing in place. And then for the exercise, we'll just briefly chat about, what it's going to take to make a snap together thing. All right, so let's have a quick look at some of the assignment submissions. I'm just going to switch to the great. Okay, so I'm gonna have a look at some of the submissions that we had. So for this one, this was about basically taking printing two pieces that would hinge together. So this was a really interesting submission. On superficially, it's super cool, right? This is I actually just want to re-illustrate here the importance of printing something the right way up. I printed this the wrong way up on the print bed, so this bottom part here didn't have any support, so this got a little bit messed up. But I thought maybe I could still lever these two pieces together, and while this looked very cool, the main mistake here is that these two parts, they printed to the same diameter, right? And because they're the same diameter, remember that when stuff goes down on the print bed itself, it's going to expand a little. So the pieces don't fit together. They needed to have just a little bit of padding here. And the design here is very, very, very cool, right? So leaving a little groove here, so the top part here could fit in it. Superb idea. It just needed to be a little bit larger. And then I think it would have worked perfectly. So it was very, very, very close. Very cool, but just needed a little bit of tweaking. The other submission that I got that I really liked was another submission. This, I believe, was from Chris, where he wanted to just look at the tolerances of his printer a little bit. So he printed out, his design involved several of these different sized threads. Different sized connectors. And in the connectors, we had same sort of fixed size piece that would go in. And what you can do then is because you've got these numbers here, you can get a quick idea of what the radii here are, and get a rough estimate of what the tolerances are going to be, right? So some of these are going to fit better than others, and you get, using these as a set of reference pieces, you get an idea of like, roughly like what is the maximum that you can get away with. So this one here, for example, is like a super tight fit, whereas the one at the top here is much looser. So, depending on different types of joins you want to do, this is a nice reference to have. Probably the only modification, that the suggestion that I'd have for this would be to take these various sort of like, I guess, wrenches, and actually have them so that they're all connected together in some sort of like radii. And that way what you can do is that you can print out one of these for each different type of material that you have, right? So let's just say you've got some silvery like metallic PLA versus plain old sort of like plain colored PLA. By printing these out and just keeping them all together, you can just have a handy reference that'll give you idea of like what are the tolerances for different types of material that you're printing. So this was a really nice design. I really liked it. I think, like I said, with a small tweak, it'd be pretty fantastic, and it's a lovely sort of like reference to have. And and it gives you an idea of like how your own the material that you're using behaves, but also it gives you a chance to profile some of the quirks that your printer has as well. So I really like that. That was very cool. Okay, I am gonna get cracking though with just on to sort of like some of the material for this week, and let's have a look at first of all breaking a model into pieces. So I'm gonna switch back to our Baby Yoda example. I keep on using him, but he's useful. He's very interesting. So remember, for a couple of weeks ago we had Baby Yoda, and I put on these silly beefy arms, and that was kind of fun. But let's just say you want to modify this model now, and what you want to do is that you want to print out the head separately from the body. Let's just say you want to print out the head from the body, and like we're going to get into a little bit later on, you want to put a pin on so the head can independently rotate. So how would you do that? So the first step, once you've taken the arms off, then I'm going to deal with them separately, is that you want to be able to take one of the subtractive objects that you have in Tinkercad, right? So they're called, I guess you can call them holes if you like, or whatever. But what you want to be able to do is that you want to be able to use one of these, and it could be the box, it could be the cylinder. You can even use the sphere, right? And change it into a sort of a subtractive type. And you move it over the region that you want to be able to subtract. And the nice thing about using a flat-edged object like the cylinder is this. So, for example, here what I've done is that I've selected the head. So if I were to then take this and I were to subtract it, I will have decapitated him, and then we've just got the head on its own. But what you want to be able to do is that you do want to be able to get the head and the body separately, but you want the split between them to be the same. So what you do before you split it is this: make a copy of that object, and then zoom back out, and then place it somewhere else. And then I'm going to move him over here. But then what you want to do is you want to take the top of that cylinder, and then you want to flip it in the other direction. You kind of want to invert it. So like I've done just over here. So then what happens is that when you do the subtraction, you're going to end up with a body part and you're going to end up with a head part, but the surface between them is going to be very exact, right? So, you've got the head here and it's sheared off nicely, but the idea being that, if you get it back into place here exactly, it's going to fit exactly where it was before, right? So you don't have to worry about misalignment. You don't have to worry about mismatch between the surfaces. So by doing that, and by doing sort of by disassembling it into smaller and smaller pieces, you can basically arrange them so they can be printed out separately. So for example, if you then print out the head separately, you may want to change its orientation on the plate, for example, so that, for example, we're not so interested on the back of the head. So you may want to take his head over here and then flip the head around so he's down at 90 degrees. So this is the part that's facing the build plate, and that's going to be a little bit rough, but you really want to make sure that you preserve the detail here, so it's a nice way of preserving that detail, or whatever. You can start making those sort of design and printing choices on individual model parts, right? So for example, when I take these arms, I may print them out in a different orientation if there's a pin that's holding them in place, for example, and I'll print them out in such a way that I minimize the amount of finishing that I need to do on the piece. I'll arrange them on the plate, so for example, the minimum amount of structure that gets generated so that it's a support structure, so you don't have to finish the bottom of the object quite so much. Any questions about that? I know I zipped through that a little bit, but this one is kind of subtle, but it's a really nice way of, like I said, splitting the model into smaller pieces so you can work with it.
No, that's helpful, because I think I was trying to do something like that.
Got
I
it.
couldn't. Yeah.
Got it. It's worth noting that somebody else asked earlier today about can you do this automatically, right? Is there a program that you can load your models into and you can automatically slice them up? And I don't know. I mean, you could try taking your model and you could take the sort of the marble sculpture approach, and you could divide it into a series of cubes. The same way that you blow up a drawing. Like you draw a grid on it and then you blow it up and you work with the individual grid pieces. You can kind of take that approach, but it's kind of wasteful in terms of material. And what you want to be able to do is that you want to be able to fit it with as many large boxes as possible, right? So one way of breaking it down is that you could imagine taking your model and then you just fit a series of boxes to it, and you use those boxes as a set of guidelines for where you want to be able to split it. You also want to, if you're going to be adding articulation to the model, so let's just say you want to take the head off and then you want to make it pivot, you obviously want to put the split along where you're going to be putting the pivot points as well. So that's a matter of personal preference. Unfortunately, like I said, there isn't a really good software approach to doing this automatically, partially because it's artistic, right? The computer's got to know where the splits are and where they're meaningful. And, we just don't have a good sense of that, right? The computer doesn't have a good sense of that. It doesn't have the same sense of aesthetics that you do. So, that largely comes down to personal choice. Okay, so let's have a look at the next thing, which is I want to show you about breaking a model into pieces, but once you've broken it into pieces, how do you then reattach the pieces back together? So I'm going to go and show you a few examples of some really simple pins and some snap pins that you can design in Tinkercad and actually print out. So the first one that I wanted to show you was this one here, right up the end. So I'm going to show you sort of like the general design for creating a pin, right? So let's just say we've got these two little blocks here, and what I want to be able to do is that I want to be able to put a pin between them so that they are, they can be precisely aligned. So the first simplest pin that you can do that will guarantee you alignment in a given direction is just creating a cube pin, right? And the way this is done is that the way you design these pins is pretty much the same every time, right? So what I'm going to do here is that we've got a pin and then we've got a subtractive box that the pin is going to go into. So I'm going to show you how to design that. So let's just say we start with a box here. And this process is going to be the same pretty much for any pin that you design in Tinkercad. So what I'm going to do is that I'm going to start with this little box here, and that little box, you can see it's sitting on top of this this here, and it's going to be a pin which sticks out. So what I'm going to do is I'm going to take this, and this is kind of important. First of all, I make a copy of the object. So what I do is that I hit Command C or Control C, and then I hit Control V, and I'm just going to move it. Oh, dang it. I'm just going to move it off to one side just for a moment. Then what I'm going to do is I'm going to take that same thing, and then I'm going to lock the object. And that's important. The reason that we don't want to lock it is that we don't actually end up accidentally clicking on it when we take this guy and we resize him. So I'm going to move this here. And for some reason, the alignment is just a little bit off. So I'm just going to fix that. Sorry, just bear with me. There we go. So I'm going to move him so he's exactly aligned. And then what I'm going to do is I'm going to change the type of this object to a hole. And this is where it gets important. What I want to be able to do is that I want to be able to make sure, remember I said about the pieces, if they're exactly the same size, they're not going to slot together. I want to make sure that the hole is just slightly bigger. Now for my printer, I find that if I want a nice sort of like smooth fit that doesn't have a lot of friction on it, but it still is a reasonably, reasonably tight fit, what I want to do is that I want to move all the pieces, I want to move all the sides away of this. I want to move them by about 0.25 millimeters, right? So what I do then is that I take my whole object now, and I'm going to drag that corner out just by 0.25 millimeters. And because I've taken this object that's underneath it and I've locked it, it means that I can select right through to the other side. So I can select that side and again, just sort of tweak it out. So what you can see now is that the box is just ever so slightly larger. And just for completeness, I'm also going to do the top as well. So what we've got now is that we've got this box, and it's just ever so slightly larger than the pin that it's going to be accommodating. So then what I do is that I switch back to my 1mm selection. The pins on this are actually quite tiny, so whenever you're doing this, you probably want to do this a little bit larger, but that same 0.25mm tolerance it's about right for most 3D printers. You may find that certain types of printing techniques like resin will allow you to have a smaller tolerance, like 0.1mm. Again, that's one of those things that you're probably just going to have to, try and just see what your printer does to really get a guide for how that's going to work. So what I'm going to do now is that I'm going to take my two little boxes and I'm going to make a copy of them so I can demonstrate how we take these pins. So I'm going to take these as well, and oh, sorry, I need to just hide that. Oh, no, I don't want to do that. It's all right. Dear gods, getting so lost here. Take these, move them back, unhide everything. Okay, take that. I'm just going to hide the top one, and then I'm going to select the one underneath, and I'm going to unlock it so I can actually select it again, and then re-unhide that. So it was a little bit of a confusing set of steps, but a little bit of practice, you'll get it. So I'm going to take those two now. I'm going to just make a copy, and I'm going to paste them, and then I'm going to move this over here. I just know that it's somewhere in the box. We can fiddle with the exact placement later on. Then I'm going to move this up here until we can see it. So what you can see here is that you can see that we've got the you can see the whole object, and you can see the little pin that's underneath. So then what I do is that I select the whole object, and then I select the box that's on top, and then I just do combine. So you can see now that the top one has a hole in it, and then I select the bottom object, and I select the pin, and then I select the bottom object, and then I combine those, And then what we've got now is that we've got these two objects. So we've got the top, which has the hole for the pin, and then the bottom one, which has the pin itself, right? So what does that look like in a practical sense? So I'm just going to switch back over to the to my little desk camera, and this is what it looks like in practice, right? So we've got our we've got our top plate, which has the hole in it, and then we've got the pin. And you know, there really isn't a lot to say about this. You know, you take the top part, and the pin just slots over the top. It's relatively straightforward, right? There's really not a lot to it. It's relatively loose, you know. So if I hold this upside down, it's going to fall right off. But in cases where you just need something to hold on to another object, and you just want it to sort of sit there, and gravity is going to hold it into place, or you do actually want it to be loose, this is a great way of going, right? So it's a really, really simple pin, and it fixes the orientation as well. And it's just a really simple, quick way of generating a pin that goes between the two objects. Now, the alternative for this then is, well, there's a few alternatives going ahead from here, right? So what you can do instead is that, let's just say you want to add a bit of rotation to this. So the alternative there is to use a circular pin instead, right? So what you do is that you use a cylinder, and you do the same trick, right? So you create the hole around it, you expand it by 0.25 millimeters on each axis, so it, you know, it surrounds it, and then you use that same technique to basically carve out a hole. And the way that looks is a little bit different again, right? So let me switch to my camera, and with this one here, again, similar sort of thing, right? So you've got the pin out here, the top plate goes on top. But with this one here, you've got a nice sort of smooth rotation around this, right? So in the cases where you want things to fit together, but you need them to be able to rotate, that's a really simple way of doing that as well. But again, this has the same problem. There really isn't a lot that's holding it into place, so it's going to fall right off. You could adjust the tolerances, so you can make it, say, 0.1 millimeters, so that it becomes more sort of a friction fit. But when you've got that friction fit, again, you run the risk of eventually over time, this could potentially wear down, and it would stop holding it into place. So if you'd like things to sort of hold together a little bit more firmly, but then have the possibility of disassembly, you can switch to instead working with pins, right? And sorry, snap pins. And the way these snap pins work is actually just going to switch over briefly to show you what the side view looks like, right? So let's just say you've got these top and bottom pieces. You can make these little H-shaped size pins. And what they have is they've got these little wings, and the wings will basically go on the ends of these little arms, and the arms will get squeezed through a narrow gap, but then when they get through the gap, the wings will fold out on top of these little ledges that will hold them in place. So you've got a bottom set of wings and a top set of wings, and what that will do is that will hold the top and the bottom halves together. So what does that look like in practice? It's a little bit interesting. So when I did this, I'm just going to apologize in advance. I kind of forgot about scale, and these things are extraordinarily tiny. I'll show you compared to sort of an X-Acto blade. I made these way too small, but you know they're good enough to prove a point. On the plus side, they really didn't take. I was kind of wondering why it only took, like, you know, 2 minutes to print, but it's because it was tiny. So what we've got here is that I got my little H-shaped pin, and then I've got the little receivers that it's going to go into. So you can see just barely inside there, there's a little shelf that those pins are going to go into. So what you do is, to get one of these in, is that you just basically insert the pins in, and then you want to get one of the pins in, and then probably squeeze down on one side to get that whole thing in. And then when you push it through, you can see that you can barely see it. You can see that the wings come out, and then the wings will sit right on where those little shelves are. It doesn't look like it'd have a lot of strength, but it does. Even at this scale, it is enormously strong, and it's a really, like, quick, easy way of putting things together. And then this one's a little bit more finicky. To get the second pin in, I've got to get this into place and then somehow simultaneously squeeze the other side as well. But with a little bit of work, you can wiggle it together, and then you can see that the wings have sat on the ledges on the top and on the bottom, and we've got this nice solid fit between the two. There's a little bit of wiggle here because there's a little bit of wiggle in the tolerances that you have, so there's lots of things that you can do to tighten that up. But the nice thing is that these two pieces now are reasonably firmly together, and this can be disassembled. It can absolutely be disassembled. I'm not sure I'm going to try this right now because it's a little bit finicky, but the idea being that if you wanted to sort of get this pin out, what you do is that you take one of the wings, you'd bend it inwards, and then you would lift this top part off. And then by bending those, by bending just one of those wings in, you should be able to lift that piece right off, right? So you've got these two pieces that are stuck together, but then you're able to sort of recover that piece and get it back out. So that's not too bad. So let's go a little bit into sort of what does designing one of these H-shaped pins look like, and it's a little bit subtle. But it's not too bad. And this is largely, somebody asked me about like what ratios do I use, what measurements do I use, and I kind of just eyeball it. And I think you probably want to tweak this according to sort of the material that you're using and the printer that you're using. But at this scale, this is what I did, right? So for these H-shaped pieces, there's really sort of two parts, right? There's the H-shaped piece, and then there's the hole which it goes into. So as far as the H-shaped piece goes, I'm just going to take this piece here, and I'm going to decompose it into smaller pieces. What I've got is that I've got one of those little triangular prism shapes that you can find in the sidebar, right? So if you scroll down here and you have a look at the basic shapes, there you go. I just got that little wedge shape here. So I just rotate it around and I put it next to a long bar like this. Generally speaking, the bar is about 4 times longer than the shape is than the wedge is wide. It's up to you. The idea being that you've got this long, thin bar so that it can be bent inwards when it's going in through the hole that it's going to sit in. And then I've also got a fairly wide crossbar that sits in between the two, I guess, like the two long eye parts of the H. The reason for that is that if it's too thin, then when you try to press those two pieces together, it's actually going to snap right in the middle here. So you want to make sure this part is pretty thick. The other measurement that you want to be able to hit is that you want to make sure that the gap between these two arms is as wide as one of these bars is wide. Now the reason for that is that you can imagine that in the narrowest spot, these two, the top part of the wings are going to be knocked together, right? So you want to make sure that there's enough room for the two of them to be squeezed together, so this piece can pass through the middle. If it's not wide enough, then what's going to happen is that when you try to squeeze it through, it's just going to get stuck because the wings are going to be too wide to pass through the middle of the hole that's here. And let's talk a little bit about what the hole looks like. So for this one here, it's actually relatively simple. So you can see that what I want to be able to do is that I want to be able to carve out the ledges, and I want to be able to carve out a channel for this to go through. Note that the channel is a little bit wider than the H is at that center there, and same thing with the ledges as well, right? So the little edge for the wings to go on. So if we decompose that into smaller pieces, you can see that the design for that is actually pretty simple. So what I've done is that I've created boxes that are the same size as the top part of the H, and then the same part as the body of the H there. And I've done that same trick, right? So I've taken those corners of them and I've just pulled them out by 0.25 millimeters. And it's the same thing with the height of it as well, right? So the height of it is a little bit higher than the H itself, because don't forget that, because if it's the same thickness, then it's also not going to pass through. Now, one of the intuitions about this is, let's just say you've done this. Why not? Why do a whole H piece when what you can do is that you can just have these arms that stick up out of the bottom piece that's here. And I don't recommend that. And the reason for that is that imagine that you've got this piece here, and in fact what I'm going to do is I'm going to move it across, right? So you've got these, let's just say you've printed this all as one piece, right? So you've got the parts of the H that stick up out of the plate. Now remember what I mentioned a couple of weeks ago was that when you are printing something, if you've got stuff that's coming up out of the plate, it's going to be significantly weaker. So the risk is that if you then bend these pins together and these pins have come up out of the plate, then what's going to happen is that when you bend them to try to go through the hole, they're just going to snap. So by having a separate piece for the pin and printing it flat on the build plate, you're going to get strength where you need it, right? So all of the strength is going to be along the arms of the pin. So what you can do is that even though these pins are super, super, super tiny, they're quite strong, right? And the strength comes from having printed them sideways rather than printing them coming up out of the plate, because there's good fusion between I guess you got good fusion between those layers, and that's where all the strength needs to be. So that's the reason why you'd want to do that. So the last the last explicit snap pin that I wanted to cover was a circular pin, and these are one of my favorites. They're really, really, really weird, but they're really cool. So switching back to the overhead camera view here, this is a view of the pardon me. This is a view of the circular pin that I designed. So what we've got here is that instead of having the H pin where it's fixed in place, what I can do now is that I've got this good amount of circular rotation that's here, but the pieces aren't going to come apart. They're really firmly stuck together. So how do we do that? It's really sort of a generalization of what we did with the H pin. And what we do is that we kind of do a hybrid between a H pin and the cylinder pin. And the way that I do that is that I take a cylindrical piece that is going to be the size of the pin that's going to go between them. So you can see that this is the central shaft that's here. And then I basically chop off the top and the bottom of it. Not a huge amount, just a little bit. And the reason for that is so that it just can be printed, right? So remember, when you're printing a cylinder on its side, if you chop off the top and the bottom, it will print out nicely. If you try to print out the whole radius, it's not going to go well. It'll just deform. It won't be great. So what we end up with is that I took this thing on its side, and I'm not going to go into the details of how I did this too much because it's a little outside of the scope of this course. But what we're able to do is that I basically just carve out a space in the middle for the H part. So I do this with the same sort of like rough spec of the same sort of design width that I use for just the normal flat H-shaped piece. And then I basically use the subtraction operator to carve out a little bit there. But then I also generate a tube. So I create a tube object by basically taking I just do a normal cylinder. I carve out the center of it, and then I turn that tube that's left over into a hole. I flip it on its side, and I use it to sort of carve out the inner diameter of this. Because remember, this has got to have a little shelf for it to sit on. Then what I also do is that I take my triangular prism shapes and I just run them down the sides here to subtract out that surface as well. So I end up with, it's more for looks than anything else. I think you could just about get away with leaving this square. I just carve out that shape there just to sort of like give it a little bit more of a pin look, and frankly just make it a little bit easier to handle as well. So then what I've got is that I've got this little H-shaped pin, and then what I can do is that I can just use that to sort of snap the two together, and that works surprisingly well, right? So that pin goes in, it sits on this little shelf here, and it's quite rigidly stuck together. And just because it's that much thicker, it's actually that much stiffer. So I actually tried removing the pin out of this, and I probably actually need some sort of proper wedge. I'm probably going to need to get like a hairpin in here and then use the X-Acto knife to actually properly get this out. It's possible to remove it, but it really is quite well stuck together. And this type of pin, because there's so much more surface area that gets contacted, it's just that much more stiff and that much more stable. So it's a really nice way of doing this. And you can imagine using a joint like this. For example, let's go back to the Baby Yoda example, right? What you could do is that you could use a pin like this to stick the head to the body. And what is cool about that is that you could take the same shape that you'd use to carve the hole in the little block here, and then instead of having the body parts have any protrusions at all, because protrusions are kind of hard to deal with and they're kind of hard to print and they make things that much more difficult. What you can do is that you can say have the head part and the body part, and you could carve a cavity with a shelf inside that object. And then what you then do is that you connect them. So you can imagine that you've got like the head part and you've got the body part, and then they've got the holes that are in them. And then you just put one of these pins in, and then you can just snap the two together, right? Admittedly, disassembling it later on is going to be very, very hard because you can't get in to sort of like bend the pins together. But if you're done with it and you want to snap it together sort of semi-permanently, you can totally do that now. And you could use these two pieces to just have it so that they will turn. And there are all sorts of like sophisticated things you can do with this to stop it, to basically with the design of the contacting surfaces to make them only say turn a certain amount and restrict their range of motion or have them slide in a particular direction. So you can get really, really, really crazy with this. So there's something that I would encourage you to experiment with if you end up getting a 3D printer, because it's a really nice way of just like I said, just adding a bit of articulation to an object. And it's just another way of designing sort of hinges, and it's another way of designing sort of articulation between the surfaces. So the last thing that I wanted to cover then was, at least in this category, was working with threads, right? So let's just say you've got two pieces and you want to connect them together with a screw thread. And this really surprised me. I wasn't really sure whether I could do this in Tinkercad or not, but it turns out you can. So I'll show you what that looks like in practical terms. So what I've got is that I've got these two pieces here. They have they've got a thread hole, and I've actually got this thread, and I've chopped the sides off it. Surprisingly, it does actually work. So I've got this thread here, and well, the screw really, and I could use these to connect them together, right? So let's have a look at what that looks like. So switch back to my overhead camera. Okay, so I actually need to disassemble this. Like I said, these pieces are tiny, but they totally work. So what I've got here is that I've got my top and bottom pieces here, and I've got this little thread, and you can see here it's quite small, but it's relatively easy to get it to sort of screw in here. So I put this in here, and I just screw it straight in. Come on, behave for me. There we go. So I can just twist that on like that. And then I could take this top piece here and screw that on. And what we've got here is then we've got these two pieces. And this is in situations where you want to adjust the distance between the two pieces, right? So you can just sort of start unscrewing this, and you can adjust the distance between the two. So this is the case where you want that connection between the two, but let's just say you want to be able to tune that distance in the future. This is a nice sort of quick way of doing that. The way this actually gets handled in Tinkercad is a little bit prescriptive, but it's not too bad. So let me show you what that looks like, right? So what you've got is that you've got your thread piece, and then you've got your thread hole piece. And the way these are handled is kind of subtle. What you want to do is that you want to make sure that your thread hole is slightly different than your the actual screw itself, and you want to make sure that on the screw, the thickness of the thread needs to be smaller than the thickness of the thread on the thread hole. The reason for that is that if they're both exactly the same, they're not going to fit together. Again, remember, things expand a little bit when they print. So if they're exactly the same size, it's not going to work. So what you want to be able to do, the parameter that you want to mess around with here is once you've designed your thread, so once you've messed around with the diameter and the pitch and the segments, the number of rotations and all of that, once that is set, when you create your thread piece, or when you create your thread hole piece, you want to make sure that the thread hole has a smaller thread scale. So I'm going to crank down this thread scale to something extreme. If you look at it on the side, you can see that the thread scale here has become very thin, right? What you want to do is that you actually want your thread scale to be around, say, 0.7, maybe 0.8, right? If you crank this up, things will get tighter, basically. And but you basically want to make sure that your thread scale is smaller by some fraction than it is on the thread hole, right? So if you look at the thread hole, the thread scale there is 1. Now, there are other parameters that you can mess around with, but if you mess around with them, there's no guarantee that as a thread and a thread hole, they'll work together, right? So if you start messing around with, say, the pitch, that's going to change things quite dramatically. If you mess things around like the diameter, that's going to change things quite dramatically. If you change the rotations, that's going to change things quite dramatically. So, you want to work, you basically want to decide what size your thread is going to be, and then you just futz around with the thread scale, and you'll be done, right? So as an example, I came up with this thread, and I wanted to print it. And remember, when you print straight up out of the plate, you are likely to end up with weakness in the piece. So again, the same thing that I did with the snap together crossbar H pieces. I laid this on its side to print it. And the way I did that was that I just shaved off a small amount off either side, and then I lay the piece on its side to print it. So this is exactly how it looks. And it seems counterintuitive that a thread with pieces missing would work, but it totally works. And this is used as sort of an industrial process. Sometimes you can actually get threads that have holes carved into them, and when you actually try, for example, like drilling with one of these, the hole actually provides an exit for the material that you drill out of an object, as an example, right? So this is a totally feasible way of modeling a thread, and when you print it, again, it just basically means that it's within the realm of possibility, and so you can actually use it. All right, I covered a fair bit of material there. I just want to stop briefly. Does anybody have any questions about that?
I know I'm gonna watch the whole thing over again and do it step by
That's fine.
step.
All right. No worries. Yeah, I know I went through it a little bit quickly, but it's a fair bit to cover.
That's okay.
So, no worries.
That's why
Okay, cool. No worries. Okay, cool. So, next topic I wanted to cover was one that's close to my heart because it's very excessively nerdy, and it's a really nice piece of art as well. And I wanted to talk about printing in place and some of the history behind it. And this one is the thing I want to talk about here are Chinese ivory spheres, and these go back a very long way, hundreds, I think, perhaps even thousands of years as an art form. And obviously, they don't use ivory anymore. But back when ivory was a material that was used for art, what would happen was that for the Chinese courts, you'd have these artisans who would design these extraordinarily elaborate ivory spheres. And what was weird and cool about them was that they were concentric spheres, and sometimes the number of layers was insane. I was reading about one that had 42 layers, and the way that these were made was that the artisan would have a go at it with something that looked a little bit like a dentist pick, right? So the kind of the pick that's used to sort of pick plaque out of your teeth, and they would slowly carve these shapes out. And the way that they do it is that they would slowly get in there, and they would carve out the inner layers, and they would carve out inside these spheres, and these patterns would interlock so that they're able to generate these fantastic objects, and these enormously complex patterns. And what was cool about it, and that would really do your head in, is that when you pick one of these up, there was no way, if you didn't know how it was made, it wasn't obvious how these spheres were fit inside the other spheres, because there was no exit on the surface of this hard ivory object that was big enough for the inner spheres to be stuck in, right? But of course they weren't. They were generated right there and then on the build plate. Well, not on the build plate, but on like in the artisan's hands. And these would take years and years and years and years to make. And what's interesting is I guess the 3D printing has made making these possible again, right? And what you do is that you exploit the fact that things go down in layers, and if you're careful about how you arrange the layers, you can basically place objects inside another, right? So I'm just going to show you an example now of what this looks like with like a really simple object here, right? So what I've done is that I've just created this little, again, like this little sort of like H-shaped object. So the way I start with is that I generate, I want to have it so that I've got this, pardon me, I'm just going to zoom in a little bit better. Okay, so what I've got is that I've got this little triangular shaped base, like a prism, and I've got this rod that's in between it. And again, what I do is that I take these individual separate pieces, I make a hole that's just a little bit bigger, and then I flip them. So I've got one side below and one side on top, and I use that to sort of carve a shape inside that object. And what's cool about this is as long as you make this gap big enough, right? So I made this gap, it's a little bit bigger than I used for the snap together objects because they're printing right next to each other. So the gap here is more like 0.5 millimeter than you typically get with the with stuff where you can snap it together later on, which is more like 0.25. But with that gap, then what happens is that these layers get printed up, layer by layer. And what'll happen is that when we are, again, sorry, just zoom in on this a little bit better. When this gets printed up, this layer is going to go down and this next layer is going to go down. And what will happen is that this object will get trapped inside the other one. So when you actually print it, it looks really peculiar, but there's a little bit of wiggle. This is one, I realized that this wasn't one of my best examples, but I'm just going to show you anyway. So what we've got is that I've got this, I've got that little object and it's trapped inside the other one, right? So I've got this object that's here, and this is a whole separate object, and it's not super obvious to the camera, but it does wiggle. There's a tiny bit of movement there, and it's about 0.5 millimeter of movement, but this object is inside another one. Now, that isn't a really useful example. It's just one object trapped inside another, and there are actually legitimately useful things that you can do with it. I just wanted to show you there, just in terms of illustrating the layers. So this one here is a captive set of cones, and what you can do is that you can create a printed in place, I guess if you like, sort of like cylinder and axis mechanism. So again, what I do is a similar sort of thing. So instead of using a sort of a prism shape, what I do is I use a legitimate cone, right? So I've got a cone hit shape here. Again, I make a hole that's just slightly bigger, 0.5 millimeter bigger on all sides. And then what I do is that I flip that cone upside down. So I've got like one cone at the bottom, one cone at the top. The reason I do that is that if I just have the cone on one side, then it's going to slip out on that one side as well. So you need to make sure that you've got a little bit of bite here to make sure that it's not just going to just slip out of place. But then what I do is that, this is just a cross-section view here on the right-hand side. The cone here then, again, these get printed up layer by layer by layer. They won't stick to each other because there's a gap between them, but when it gets printed in place, it gets printed in place. And this is a captive mechanism. So I'm going to show you what that looks like. So this is the captive mechanism that I generated from that. So you can see that there's a little bit of wiggle here. Not a lot, but there is a little bit of wiggle. But significantly, what I can do is that I can hold the cylinder part, and this freely rotates. It freely rotates. There is no issue there. When I got it off the build plate, there was a tiny bit of stick, but as soon as I got it off the build plate, I just gave it a couple of shakes, and then it's able to completely freely rotate. So this is something that you can print on the build plate, and there's no assembly required. So, if you are careful about how you design your mechanisms, if you're into building mechanisms, you can actually print mechanisms right there on the build plate that require no assembly, right? So you take it straight off the build plate and it's done. And this is really useful if you are making a lot of the same thing. So right now, one of the designs that I'm working on is I've got about half of the joints in a leg mechanism that I'm building, right? So I'm building like a really small, simple walking robot, but it's got this fairly complex walking mechanism with a lot of joints. And it kind of annoys me that this thing that I'm building has got something like 16 legs. And it kind of annoys me that I have to snap each leg piece together. And I am working on an alternative design where you don't have to snap each piece together, right? So the leg mechanism, when it comes off the build plate, my eventual goal is to have it so I can lift it straight off the build plate and I don't have to snap anything together. I can just take this entire leg mechanism and then attach it to the power, and then off it goes. So but you can also do sort of artistic things with this as well. So I wanted to see, like, could I quickly come up with an approximation of the Chinese ivory carving? So could I try just doing one level of that using Tinkercad? And it turns out totally possible, right? So coming back out here, this is an example of what I did. So what I did was that I took a cube and I wanted to put a sphere inside it that wouldn't otherwise fit. So the process there was relatively simple. I created a sphere that was bigger than the cube, made sure it was all lined up. Then I used it to carve out a hole, and then I placed in another sphere that was a little bit smaller. Again, the gap here that I used was 1 millimeter. Arguably, I could have gone with 0.5 millimeters and it probably was fine, but I was just being a little bit conservative there. And then to make sure that it would print, I took the bottom surface of the sphere and I just made sure that it would sit flat on the plate, right? So I'm just gonna briefly unpair that so you can see I just basically shaved off the bottom so that it would fit together. So how did that all work out? Mixed result. I'll show you what that looks like. So my first print really didn't go very well because these bars, which when they were coming off the print plate, were a little bit too thin, right? So I had bits that would snap off, but the ball is still completely captive, right? So this ball doesn't look like, there's no obvious way that it could have been fit inside this, and it totally worked. Now, I had a hunch that if I printed this at 2x, I wouldn't have the same problem, and I was almost right. I still somehow managed to have one piece break off, but at 2x the scale, it's still a reasonable demonstration of an object that's stuck inside another object. And you could very quickly figure this out for yourself in Tinkercad, right? So if you wanted to, you could probably come up with your own design of one object that's stuck inside another, and then use that to sort of generate several concentric objects and print them right there in place. It's kind of a fun thing to do, and it's very satisfying from an art point of view. I can tell you that for sure. So, all right. Before I just quickly go into the assignment, do I have any questions?
Actually, when you were talking about that, I grabbed something I wanted to show you.
Awesome.
I've had this for a really long time. If you can see what it is, it's very
wow.
heavy, but it's got an elephant inside an elephant inside an elephant.
Oh,
And
that's
this was
amazing.
hand done. It's very heavy, some kind of I don't know,
A clay
ghost
thing.
stone or something.
Yeah.
Yeah. Isn't that cool?
That is awesome. There you go. Another example of that. That's so cool.
Yeah. Yeah.
Love it.
I've always wondered how the heck did they do that? They worked with these little tiny knives and sculpting
That
tools.
is that is so cool. Yeah, I'd imagine it would have taken a long time. It got me thinking about if you're an artisan 600 years ago and each piece of art that you made took you a year to make, how did you live for that year? It makes me think about how artists get paid today, and things probably haven't changed all that much, sadly. Anyway, anyway, all right. I had a question. I had a couple of questions from Seb. So he's not in front of a computer right now. The thread scale. Would you want to scale the diameter a little? Yes, probably. So when going back to the thread pieces here, I'm just going to go back to this. Would you want to change that thread a little, that thread scale a little? Yes, probably a tiny bit. You probably want to sort of scale it in each dimension. So you probably want to take this piece here and maybe just sort of scoot it over a little bit. You don't have to, though. I found in practice in Tinkercad, there's something about the way that it computes the geometry that it does make the hole a little bit fatter automatically. But again, that's sort of a little bit sort of like you probably want to finesse that a little bit by yourself by hand. It's hard to sort of like know what the right thing to do is until you printed something out and you've seen how it's gone. Also, for your assignment piece, I see, okay, right, you did have a gap in your assignment piece, but it was 0.1 millimeters. Yeah, that was probably it. So 0.1 millimeters is probably smaller than what my printer expands to. So I think it was probably 0.25 millimeters. It would have worked great. But it was a really, really neat design. I really liked it. So that's that. Okay, I'm just going to briefly cover the assignment. So for the assignment this week, and this will be the last assignment because next week is going to be our last class. I think what I'd like you to do is I'd like you to have a go at making a pin, right? So let's go back to this one here. So I'd like you to sort of you can decide how much you want to bite off in terms of complexity here, but have a go at making one of these types of pins, right? So even if it's just a simple sort of square pin or a cylindrical pin, go for it. If you're feeling adventurous, make a H-shaped pin and just have it so that you've got a pin that is holding two things together. And if you really want, go crazy and try making a circular pin. That's an interesting challenge. But yeah, have a go at that, and then send me your results, and I will try printing them. And then when we get to the class next week, let's actually try sticking them together and see which ones work and which ones don't work. And I'll let you know for my printer then. So you've got the parameters now. For my printer, I found that with Tinkercad designs, if you have them so that the tolerance is about 0.25 millimeters. That's about right, right? That'll give you a nice sort of big, comfortable amount of space, and it's not so big that things are going to automatically start slipping when you start assembling those pieces. So please have a go at that, and then if you get that to me by Wednesday, I'll try printing them out, and then I think we're done. So next week, let me have a look at what we are going to cover. So next week, what we're going to cover is we're going to cover the submissions. We're going to have a look at finishing prints, right? So I'm going to show you basically sanding prints, painting them. It's one of my favorite topics. It's like, really sort of like getting like a pro finish on a model. What does that look like? What does it take? Sort of like filling in holes and printing it. How do you even get it done? So I'm going to have some examples of like the different types of paint finishes that you can put on a model as well, and what works well with. I mean, since most people are going to be working with PLA, I'm going to focus on PLA a little bit, right? So how do you finish your PLA prints and sort of smooth out some of the artifacts that you get when you typically 3D print things? And then I'm also going to have I'm going to show you some of the other workflows, right? So what comes after this, right? So once you're done with Tinkercad, once you found the limits of what you can do, what does it look like to design something in, say, something like a 3D package like Blender? And what does it look like to do design in something like Fusion 360? And then we should have a little bit of Q&A after that, and then I think we'll